So, we are discussing the combination of uniform stream and infinite line doublet and infinite line vortex, or in two dimensional sense a point doublet and point vortex. We show that the resulting flow is a flow about a circular cylinder with circulation. We have considered deliberately a clockwise circulation. The idea is why we have considered clockwise circulation, so that we want to have higher velocity on the upper part of the cylinder than the lower part of the cylinder. We have seen without circulation the flow about circular cylinder is perfectly symmetric. The flow velocity on the upper half and the lower half are exactly identical. We have used a clockwise circulation. As a result, you can see, if you look to the velocity expression which we have written on the cylinder surface, we have written, say, let us write it uniform flow plus point doublet all in two dimensional sense and I think the velocity expression we computed, the velocity expressions were on the cylinder surface and the tangential component of the velocity is and this of course satisfies the boundary condition that the radial component of velocity, which itself is the normal velocity, is 0 and this tangential velocity. Now, let us first locate the stagnation points. Now, UR is 0 at all points on the cylinder. So, at the stagnation point what we need is that u theta should be 0. So, at the stagnation points u theta equal to 0, and if the stagnation points are denoted by theta s, then what is theta s? What is the location of the stagnation points? Yes, sin theta s equal to this gives the location of the stagnation points. So, where will these stagnation points be if we Where are these stagnation points? Third and fourth quadrant. So, there will be two stagnation points or the third and fourth quadrant. Okay. So, here let us take it, one is here, the other is let us say here. Okay. And the streamlines will be now this. Now, this of course, we cannot say what will be the exact value of gamma. We have nothing here to say what should be the value of this circulation gamma, because we really do not know that for a given cylinder where will the stagnation point be. So, depending upon the value of the circulation gamma depends on the location of the stagnation point or vice versa. The location of the stagnation point depends on the value of the circulation. Without knowing one, we cannot definitely say what is the value of the other. As an example, if gamma is equal to 4 pi r u infinity, what will happen then? See, this is what we have seen when gamma is less than 4 pi r u infinity. This is the situation when gamma is less than 4 pi r u infinity. If now gamma is at 4 pi r, gamma equal to 4 pi r u infinity, then you see that this sin theta s has value -1, meaning that both the stagnation point will be then here. The two stagnation point now coincides here, and if we want to have some streamlines, these are the flow streamlines. Two stagnation point now coincides. If the value of circulation is higher than this, there will be no stagnation point on the surface of the cylinder. The value of theta is then imaginary, However, the stagnation point as it happen, it will come down on this particular axis, but below the cylinder. You can even show a situation that you see we have here a circular streamline, some circular streamlines around the cylinder. So, you see that means that the fluid here in this part, fluid in this region will not flow, it will just rotate with the cylinder, rotate around the cylinder. So, these are not imaginary situation, though of course, the situation differs slightly, but this can happen. This circular cylinder with a circulation, you can create that flow just by a rotating cylinder. Flow about a rotating cylinder or a spinning cylinder is an example by this, and where that rotational speed of the cylinder will represent this circulation. As you can increase the rotational speed by which is equivalent to this gamma, you can create all these situations. Even you will find that if you increase the spinning velocity of the cylinder or the rotational speed of the cylinder, a situation will come when some fluid close to the cylinder will just rotate with it, it will not flow, because that corresponds to this situation, or the streamlines representing the general flow, they are these, but there are some fluid within this closed cylinder, closed streamlines. Now, the general nature of the flow, see there are many practical examples also, and some of these perhaps you have heard of it or you have used it, you have seen it, maybe in case of a cylinder or sphere. Okay, as you have seen in that non-circulation case, without the circulation, for sphere and cylinder we have seen what is the difference in the flow pattern. As such, the flow pattern is similar, only in 3 dimension case it is the flow is little relieved, not as much stressed as in 2 dimensional case, because of the additional direction available to it. So, when there is circulation also the same thing happens, even in the presence of circulation that 3 dimensional relieving effect is present, rather that is always present 3 dimensional relieving effect. However, this basic nature still remains the same, and you have often heard of that swing of cricket balls and all, they are all example of this, where some sort of rotation is introduced to the ball, so that it behaves like a spinning sphere or rotating sphere. Even in the earlier days of navigation, long back, few hundred years back, people used this effect to propel ships or boats. By rotating a cylinder. Even nowadays rotating cylinders are used, say there are some high speed automobiles which used rotating cylinders to reduce fuel consumption. The basic principle is this, you will see that this will now produce a lift force. Again lift force is in the direction normal to the flow. So, what we call lift, sometime it can be even side, rather in case of a swing of a cricket ball, that lift force is basically a side force, but again it is normal to the flow direction. Anyway, let us now write the pressure coefficient. What will be the pressure coefficient? Pressure coefficient pressure distribution or pressure coefficient on the surface of the cylinder. At far away we have P infinity plus half rho u infinity square, we are not writing rho infinity, there is no point, is on the surface of a cylinder. Let us say at any point pressure is P and the velocity is, the radial component is 0, only tangential component gives the total velocity. So, how much is that? Half rho, how much is that velocity? Minus 2 u infinity sin theta minus gamma by 2 pi r. So, what it will be? P minus P infinity C p equal to P minus P infinity by half rho u infinity square 1 minus is 2 u infinity sin theta plus gamma by 2 pi r square divided by u infinity square. Okay. So, how much is that? One minus 4 sin square theta term is already there, which was the Cp for without rotation or without circulation, and in addition what we have? Minus gamma square by 4 pi r u infinity square, 4 pi square r square u infinity square minus much it is coming? The additional term minus 2 sin theta 2 sin theta by pi r u infinity into gamma, these two additional terms. Okay. The pressure distribution is now no longer symmetric on the top and bottom. Now, calculate again the lift force. Lift force per unit span. What it was 0 to 2 pi minus p minus p infinity r sin theta d theta. You can substitute what is p minus p infinity and complete this integration. How much it is coming? Yes, carry out this integration. Yes, how much it is coming? Hmm? 2. No, the 2 will not be there. 2 will not be there. So, we have got this very important result and very general result that lift is rho u infinity gamma, or most importantly that lift is linearly proportional to gamma. So, you see the importance of circulation. And you have seen the purpose of these doublet, source and vortex. What you have seen that doublet, source, vortex, they are singularity in the flow, and in incompressible flow also you have seen that there cannot be any expansion, where source and sink are basically expansion, singularity and expansion. But you see now we do not have source or sink in the flow. The source or sink we are just imagining at the center of the cylinder, that is all. It is in our imagination. Even the singular vortex is also in our imagination. We are assuming that there is the effect of the cylinder is such that we have a point doublet and a point vortex at the center, that is all. So, it does not mean that flow about a wing, later on we will see that flow about a wing also will be getting through source, sink, doublet. Okay. That does not mean that in an aircraft wing, if you open the wing, you will find some source and sink. Those source and sink are in our imagination, we are assuming that is the effect of the wing. Can you find the drag force? Again you can integrate same thing, only cos theta, that p minus p infinity r sin, instead of r sin theta it will be r cos theta now. Yes, how much is the drag force? How much? 0. That is the failure of classical theory, that no matter whatever you do, a two dimensional ideal flow will give 0 drag. And one need to think that perhaps two dimensional ideal flow assumptions are not adequate. We have come here through some assumptions, no? We have assumed that the flow is incompressible, flow is inviscid, flow is irrotational. Obviously, there is some flaw somewhere in those assumptions. We have assumed that the flow at very high Reynolds number, the viscous effect will be confined within a very very thin region, which is basically negligible over the, when we consider the entire flow field. When we consider the entire flow field, then that very very thin region near the body is really negligible. And we see that as far as finding velocity, at least if not for circular cylinder, because the circular cylinder case is a little different, even though we have solved the flow for circular cylinder, but we will tell why circular cylinder is a little different from others. But when we apply this to say airfoil like bodies, we really get very good result as far as lift force is concerned, even the pressure field, velocity field, but when we come to drag, it gives straight away 0, even for a circular cylinder which has a very high drag coefficient. Usually this lift and drag, they are expressed in terms of coefficient, which we have defined earlier. lift coefficient is lift force divided by that half rho u infinity square into an effective area. For a wing it is used planform area. For cylinder, for a finite cylinder of course, again you can take the planform area. For an infinite cylinder usually unit width is considered. So, it is only the area is simply diameter into 1. So, that when you divide this lift or drag force by that gives the lift coefficient or drag coefficient. Say you can write C L as lift force by half rho u infinity square s. Similarly, C D is S is that planform area usually or some reference area. So, in this case of course, we find C D is 0. C D is 0. For wing or so, the usual C D is of the order of 0.01. So, instead of 0.01, if we get 0, you can say okay, it is perhaps very close to it. But in case of a cylinder, the C D is of the order of 1 or even higher. Of the order of 1 or higher, that also you are getting 0. Eventually, anything we try, C D will come to be 0, the drag force will come to 0. The reason at this stage I can tell you that what we have neglected is one boundary condition, not that we have dropped one term in the equation, that is not that serious. The serious thing, because you have dropped one boundary condition, we are not satisfying no slip boundary condition. On a body surface, we have said that normal velocity is 0, but in actual case in real viscous flow it is both normal velocity as well as tangential velocity, both should be 0 on the body surface, which we cannot satisfy in our inviscid flow calculation, because we have dropped that second order term. As a result, we are not been able in a position to satisfy two boundary conditions. So, even though viscous effect is really small, the effect is really small, as far as lift is concerned, the effect is really small. It hardly changes the lift coefficient, maybe a few percentage, 5-6% decrease in lift coefficient because of that viscous effect. So, as far as lift is concerned, this theory gives a very good estimate of lift, only a small error, but as far as drag is concerned, it gives 0. Of course, later on when you go to 3-dimensional computations, we will not do it here. You will see that we get a different type of drag, but that is altogether a different proposition. Okay, now what else? Okay. Similarly, superposition of these singular solutions or basic solutions, we can produce some other flow features or some other important flow, but we will not go to this. We will conclude this discussion with this warning that okay, we can get flow about certain bodies by just superposition, but to give when you have given a certain body That means, if you are asked to find the flow over a certain body, you are given the body, you cannot say what superposition you are going to use. Okay. Here it is, okay, we have a combined uniform stream and a doublet, we have got a cylinder. But given any general shape, you cannot say what should be the combination straight away and cannot write this. So, if you are interested in finding flow about an airfoil and wing, in general you will not be able to say that what should be the combination or what should be the correct combination, or whether there is only one single combination that will give us the flow about a airfoil or wing. In this case, as it happens that it is more or less like an accident, that we have assumed, we have combined something and which we have seen satisfying some boundary condition, like a uniform stream and doublet, okay, it satisfies the boundary condition for flow about a cylinder. We did not know it before starting. Okay. Similarly, for a Rankine oval, we have seen that, okay, we have a uniform stream, source and sink, that satisfies the boundary condition for an oval shaped body. So, we took that to be the solution of an oval shaped body. Now, given an airfoil, again the boundary condition is that normal velocity is 0, normal component of velocity on the airfoil surface is 0. Of course, now this boundary condition become complex because of the direction of the normal, which is changing from point to point. Of course, we can write what would be the mathematical expression for that, but anyway this boundary condition is now little much more complex than the earlier boundary condition, where it says that radial component of velocity is 0 for a circular cylinder. So, what we see that for a given body, it is usually not possible straightforward manner to specify what should be the combination of the basic solution. If we want to do it, we have to assume some sort of combination and then forcefully satisfy the boundary condition to find what would be their strength. That approach, of course, we will be doing in the next course, not in this course, where for any given body we will just assume some sort of distribution, whatever you feel like, and then force the boundary condition on it, so that we get the appropriate strength and your flow problem is solved. Okay. But that needs a numerical technique, it is not an analytical technique, it is a numerical method. However, alternately we can think that the solution that we know, if by some mathematical technique from this itself we can find the flow about another body. Like say we know the flow about a circular cylinder, lifting, non-lifting. When there is no lift, the flow is called non-lifting. When there is lift, the flow is called lifting. So, we have both lifting flow, non-lifting flow. Lifting flow is uniform stream, doublet, vortex. Non-lifting flow is uniform stream plus doublet. Now, if we can somehow transform this cylinder to another body, let us say we are interested in airfoil. If we can transform this cylinder to an airfoil, and consequently the flow field is also transformed by that transformation, then our solution is complete, we have the solution. And this was one approach pursued long back, and we will consider one such approach, one such transformation technique, by which we will be able to transform the flow field about the circular cylinder to flow field about an airfoil. However, to apply that transformation, we will again go back to our complex analysis. If you remember, earlier we talked about that by definition the stream function and potential function satisfy the Cauchy-Riemann condition for analyticity. If you remember that u equal to d phi dx equal to d psi dy and v equal to d phi dy minus d psi dx, which implies that phi, which is a function of x and y, and psi, which is also a function of x and y, that phi plus I psi is that this f is an analytic function of z, that phi plus I psi is an analytic function of x plus I y. That is what the meaning of this. In terms of complex analysis, the meaning of these is phi plus I psi is an analytic function of z, where z is x plus I y. And then we defined this f z to be the complex potential and d f d z to be the complex velocity, which happens to be u minus I v. So, f z is complex potential and we defined w z, I think, where we write remember this is, even though we are calling complex velocity, it is not u plus I v, it is rather u minus I v. This complex analysis is of course restricted to only 2 dimension, we cannot use it for 3 dimension. Now, any function can be thought of as a mapping, any function can be thought of as a mapping, even your simple function y equal to x square. With this you map x onto y, x become y because of this transformation. So, it is a transformation. So, any function as such can be thought of as a transformation. So, if we have a complex function of z, say another complex function of z, let us say zeta z, where zeta is xi plus I eta, let us say zeta is so, this is a transformation, this is a transformation from z, and we can call it like say z x y defines a coordinate plane, which we call the z plane. In the complex analysis, that is what is called the z plane. Similarly, this zeta plane, in which xi and eta can be thought of as the coordinate directions, x and y are the coordinate axis or coordinate direction in the z plane. Similarly, xi and eta can be thought of as the coordinate axis in the zeta plane. So, this function zeta equal to zeta is a function of z transform z to zeta, like the function y equal to x square transform x to y. Similarly, zeta as a function of z transform z to zeta. So, if we have a curve in the z plane, it will be transformed to another curve in the zeta plane. Now, let us say this transformation function is a analytic function. The function which is used for transformation is an analytic function. Then what can you say about the property of the transformation? Yes. The complex number z x plus I y represents a point in the z plane. Similarly, the complex number xi plus I eta represents a point in the zeta plane. A point in a transformation, of course, the transformation need not be one to one. There is an one to one transformation and one to many or many to one. There are different type of transformation. One to one means for a single point, if you get only single point, it is 1 to 1. If your transformation is such that for each z point you get one zeta point, then it is 1 to 1 transformation or 1 to 1 correspondence. But you may have one to many. For given one given point you may have 2 points, like as simple as that y equal to root x. If x is say 4, for y you get plus minus 2 both. Okay. Y equal to x square is many to 1. You give x equal to plus 2 or minus 2, you get y equal to 4, many to 1. So, all transformation can be different type, but say for the time being let us consider that 1 to 1 for simplicity. So, if you have one point in z plane, by this transformation we will get one point in zeta plane. So, if you have a curve is of course just a combination of a set of points. So, we will have another set of points in the zeta plane which will also give a curve. The shape of the curve may be different. Now, what we are saying that this function, the transformation function is analytic function. They satisfy a very special property. What can be that property? You have already have a course on complex analysis. Laplace equation. Cauchy-Riemann condition is the condition for analyticity. Whether a function is analytic or not, you check it by Cauchy-Riemann condition. What is that? We have already written for phi psi. the most important property of transformation through analytic function is that this transformation is angle preserving. This transformation is angle preserving, it preserves the angle. As an example, think about you have two intersecting curves. Let us consider that you have two intersecting curves. If you transform it, again you will get two curves, but in general transformation that those two curves may not also intersect, is it? But if it is one to one, they will definitely intersect. They will intersect after the transformation also, because the point of intersection will be transformed to one point only. They have to lie on both the curve, and after this transformation the angle between the curves will remain the same. So, now think about these two curves. These two curves need not be an isolated curve, even one curve can be thought of as intersection of two curves. What we are seeing as one curve, say arc of a circle, to you it appears as one curve, but I can think that it is also intersection of two curves, interaction of two curves. Half of the arc I take as one curve, another half I take as another curve. So, at any point we can think that two curves have intersected, and the angle there will be preserved. Try to think what will be the implication of it. Transformation through analytic functions have a very popular name, it is called conformal mapping or conformal transformation. Okay. Transformation by analytic function is called conformal mapping or conformal transformation, and the literal meaning of conformal is angle preserving. That is why this name. Think it this way now. Think about that you are transforming one curve in the z plane. Let us say in this z plane this curve is a circle, and you are transforming it by a conformal transformation or by an analytic function. At each point on the circle you can think that two curves have intersected, okay. And after transformation these two curves will again intersect and the angle will remain same. What type of curve you can get? Same shape? Not necessarily. The shape is preserved in infinitesimal sense, not in large sense. An infinitesimal portion of the curve will retain its shape. So, an infinitesimal straight line will remain as infinitesimal straight line, but when it becomes finite it may change. It will remain closed, definitely, it will remain closed. Infinitesimal shape will remain same, but size need not be. The size need not remain same. Then now can you tell what can you get? Yes. at any point on a circle two curves are intersecting at an angle phi, the angle is pi. After transformation also it will intersect at pi if it is a transformation through an analytic function. The shape in the infinitesimal sense will remain same, that is infinitesimal straight line, and infinitesimal part of the curve is a straight line. It will remain straight line, but its size may be changed. It will become an ellipse. Circle is of course a special case of ellipse only. Anyway, we will continue this in the next class. Conformal mapping.